When you first try fluid simulation, one thing quickly becomes clear. It's hard to turn chaotic particle motion into something that resembles the behavior of a fluid. I'll introduce you to position-based fluids, a relatively beginner-friendly technique to simulate fluids right in your browser. I want to try and make fluid simulation approachable, even if you're just getting started. In the physical world, even a drop of fluid, for example water, is made up of an astronomical number of molecules. And given that we only have finite computing resources, it's not feasible to recreate a liquid with one-to-one level of realism. However, we can approximate fluids by representing them as particles. These particles represent small fluid volumes that interact to exhibit collective behavior that mimics fluid motion. This particle-based approach is also used in other methods like smooth particle hydrodynamics and peak flip, each differing in how they compute forces and update particle positions. Position-based fluid simulation involves 3 steps in each update loop. First, we predict a temporary particle position given its velocity. Then in the second step, we ensure that particles reach a target density so that they are packed closely enough to resemble a fluid. If particles are too close, they are compressed. If too far apart, they are too sparse. We iteratively make small corrections to each particle's temporary position to satisfy the density constraint. Instead of checking the relationship between every particle and every other, an approach that is computationally expensive, we only need to check neighboring particles within a predefined radius. To optimize this, we use a spatial grid to efficiently partition space, reducing the number of particles to check for neighborhood interactions. And then when adjusting a particle's position, we only consider other particles in its neighboring cells. Adjusting each particle's position 2 to 4 times per update loop generally gives visually satisfactory results. After these iterations, the particle positions now become final. In the last step, we use the particles' final positions to calculate their velocities. Then, forces such as gravity are applied to influence the particle's motion in the next update loop. Optionally, you could apply color to the particles based on their velocity to enhance the visual effect. Now let's take a look at how you might implement these steps. I'll be using Three.js with Vite, but you could easily just use vanilla canvas instead. I chose Three.js because I do plan on optimizing the code and creating a 3-dimensional simulation in future. I do have a Three.js tutorial in case you'd like a jumpstart. Let's go ahead and import Three.js into a script. Then we can quickly set up a Three.js scene. This is the HTML I'm working with, and I have a container for the Three.js canvas over here. Then we need to initialize a bunch of simulation parameters we're going to need, and we shall talk about them as we move along. We've discussed how the grid helps efficiently locate neighboring particles. It's going to be made up of an array of cells. Each cell class has an array of neighboring cells and the particles within it. And then this is the code for establishing neighboring cells. We'll be placing particles into the cells during simulation since they will be moving around. Let's also go ahead and create a Three.js plain object and only show the outline. This outline is going to mark the boundary of the fluid, otherwise known as the fluid domain. This shifting around is there to ensure the origin of our coordinates is at the bottom left of the plane. This plane is going to be the parent of our particles, meaning they will use this coordinate system as well. Speaking of particles, let's go ahead and initialize them as Three.js sphere objects. You might want to use Three.js particles with a custom shader for efficiency purposes, but let's keep it simple. Three.js provides a user data object where you can store custom data. I'm using it to store particle properties. The main part of the simulation is the simulate function, which will be called recursively in the animation loop function. And finally, we refresh Three.js parameters in case the user resizes the window. So now with all the basics out of the way, it's time to talk about the simulate function. We begin by predicting a temporary particle position based on the particle's velocity. The velocity vector of a particle tells you by how much a particle is being displaced in a particular direction per unit time. By multiplying it by delta time, the amount of time since the last update, we get a displacement amount which we can add to the current particle position to get the predicted position. I've set the delta time to a fixed number. Since we are working in 2 dimensions, we perform this operation for both x and y velocity components. With the predicted particle positions, it is unlikely that the particles have uniform target density throughout. We need to make multiple particle position adjustments to satisfy the density constraints. The reason why one iteration is not sufficient is because every particle is getting a position adjustment based on other particle positions before the adjustment. So you need multiple iterations to get good results. 2 to 4 times is enough. Let's clear particles within each grid cell and then place each particle in the appropriate cell based on its position. We already determined the density we want for our fluid. What we need to do now is to determine by how much the current particle deviates from the target density in order to make the necessary corrections. The closer a particle is to its neighbor, the denser the fluid is at that location. To determine exactly how dense, we sum together the product of the particle's mass and the value of a smoothing Carnot function. The particular Carnot function I chose is called the spiky Carnot. This is the formula for it. H is the maximum influence radius within which 2 particles can affect each other, and R the actual distance between them. Let's create a function for it. The function is going to take 2 particles and spit out a value based on the distance between them. The closer 2 particles are, the greater the value of the smoothing Carnot function, and thus the greater the density. To determine the deviation from the target density, we divide the current density by the target density or rest density and subtract 1. This gives 0 when the fluid is at rest density. So now to determine the adjustment we need to make to the particle's position, we are going to use this formula. What the formula says is that we are to sum up the gradient of the smoothing Carnot for all neighboring particles. The gradient is actually a vector which you get by differentiating the Carnot function with respect to r, which is the distance between the 2 particles, and then multiplying by the vector that is the difference between the position of the particle and its neighbor, and normalizing by dividing by r. And in fact, let's write a function for it. Now this lambda term, which we are multiplying with the summation, is called a Lagrange multiplier. The Lagrange multiplier scales the gradient sum to compute the adjustment needed for the current particle's position. We calculate the Lagrange multiplier by taking the negative of density deviation that we've already calculated and dividing it by the sum of the square of the magnitudes of the gradient vector of our Carnot for every neighboring particle. We also add a small value to avoid division by 0. So let's now calculate the correction we need, and then loop through all particles, applying the correction to the predicted positions. Once we've looped through position prediction a few times, we then determine a particle's velocity using the predicted position and the current particle's position. The formula for velocity is displacement over time, and so we can calculate it like this for every particle. We also need to account for external forces like gravity. Now the formula for force is mass times acceleration. So if we divide the force of gravity by the particle's mass, we should be able to get the downward acceleration of the particle. Acceleration can be described as the rate of change of velocity with respect to time. If we therefore multiply acceleration by delta time, we should be able to get an amount by which we can adjust the particle's velocity to account for gravity. Something else we need to account for is the fluid's viscosity. Viscosity is defined as the ability of a fluid to flow. We can simulate it by letting the particle's velocity be influenced by the velocities of its neighbors. And we use the spiky Carnot function we created earlier to determine the influence amount. We then calculate relative velocity, which is essentially the difference in velocity between a particle and its neighbors. Relative velocity is then multiplied by influence and scaled by a viscosity factor. So we're using the viscosity factor to control how viscous the fluid is by controlling how much neighboring velocities affect a particle's velocity. Viscosity adjustments smooth out velocity differences by reducing a particle's velocity and proportionately increasing the velocities of its neighbors, helping to equalize the flow between them. Let's go ahead now and set particle positions using the predicted positions and apply boundary conditions to ensure particles do not go outside the fluid domain. The final thing I did was to set particle colors based on the magnitude of their velocities, like so. My name is Francis. Thanks for watching, and I'll see you in the next one.